hydrogen, helium. So you can see, generally speaking, they're in the ballpark of 22 something, but there is a small variation, especially these two gases there. You can see 22.4 is not really a constant for real gases there. Real gases, they have slightly different volume. Okay, that's because of the interaction, because of the volume occupied by the gas molecules there. Okay, and chlorine happens to be a little bit bigger, 70 grams per mole. That's the molar mass there. So they occupy a little bit more space. As a result, the volume of the gas equals to 22.4 minus whatever volume of the molecules occupied. That gives you 22.06. Okay, so in this case, if you measure the molar volume versus the pressure there, the ideal gas would be this red line there. Okay, when you increase the pressure, when you increase the pressure and versus the at a higher pressure there, the volume, the molar volume there is actually decreasing. Pressure and volume are inversely proportional. So when you increase the pressure, the volume is supposed to decrease. According to the ideal gas law, the volume is decreasing along this red line there. But for the real gas, argon, you see a small deviation, especially when you exceed the temperature, when the pressure exceeds a certain amount there. So you can see somewhere around 200 APM, that's a very high pressure there. You have to go down 2,000 meters and more than a mile into the water where you have that kind of pressure there. Okay, so as long as it's below 200 APM, there is no real difference between ideal gas and the real gas. But when the pressure goes beyond 200 APM, very high pressure there, you start to see deviation. Those deviations will actually generate a problem in real life situations. In chemical plants there, sometimes when you conduct a chemical reaction, it requires a pressure to go that high, beyond 200 APM. You can no longer use ideal gas law. So if you plot PV over RT, PV over RT equals to what? N, right? So N equals to PV over RT. And in this case, for the ideal gas, you wouldn't with the straight line. But for real gases there, you will see deviation there. So obviously, the ideal gas law, the assumption of that ideal gas law, the assumption that we made about the ideal gas law, when we go to the extreme condition, no longer applies. We have to make a correction. And a Dutch scientist, Van der Waals, he actually studied many of these different kind of behaviors there. And you will see later on when you get into Chem 102 organic chemistry there, and you will see that you will hear the term Van der Waals forces. Well, the interaction between the molecules of different substances there, and he did a lot of study on these different types of issues there. So we, in honor of this research there, we call intermolecular forces as Van der Waals forces. Okay. So he studied all these different types of forces there, and he made corrections for the ideal gas law. The volume of a particle, gas particle, we have to take that into consideration. We can no longer, especially under extreme condition, very high pressure, very low temperature there, you cannot assume the volume of the gas particle is negligible. No, they're not. You have to take that into consideration. Also, the pressure interaction between the molecules there, between the gas molecules, and you have to take into consideration that. So he made some corrections there, and he made some measurements in the laboratory for each of the real gas. And this is the new form of the, we won't call it ideal gas law, the correction of the ideal gas law. That is, it still takes the form of PV equals to nRT, but we have to add a correction factor in the pressure because of the intermolecular forces, intermolecular interaction. Okay. We have to add a correction factor for the volume. Volume of the container, when you deal with volume of the gas, you have to use the volume of the container, you have to subtract the volume occupied by the gas molecules. And each gas molecule has a different size. So that still equals to n number of moles times R times P. So you may look at that equation and say, wow, that's a much more complicated equation there. And it still takes the form of PV equals nRT. And for the real gases, the A value, the V value, those are N still is the number of moles. V, capital V, and that's volume. Okay, A and B, A is the correction for intermolecular forces. B is the correction for particle volume. And for each different gas, we have a different correction factor. So when you're dealing with, under extreme conditions, very high pressure, very low temperature there, when you're dealing with, say, hydrogen gas, helium gas, neon gas, and xenon gas there, these are the numbers you need to plug in into this particular equation. And the gas law equation takes this particular form, and you need to plug in the A values and B values when you do the calculation. Otherwise, you end up with the inaccurate result. Now, these are experimentally determined values for each of the real gases there. Now, if we ever ask you to do a calculation, we will give you, involving one of the real gases here, we will give you the A equation, A value and B value there. The equation will give you the equation there. Okay, so what we want you to know here is that why does the real gas deviate from ideal gas behavior? Well, because of the assumptions that we made for ideal gas is no longer valid under extreme situation. And in those situations, we have to add the correction factors for the pressure, for the volume. So this is the what we call the van der Waals equation for the gas law, van der Waals gas law equation there. Okay, so that pretty much covers everything that we need to talk about in chapter 5, and I think I'm right on target, 8 minutes before I'm supposed to finish for today's lecture there. So I want you to keep working on the homework number 2, and take the time and read chapter 5, and we will not have exam number 2 tomorrow. Exam number 2 that covers chapter 3, 4, and 5 is going to be on next Tuesday. There is a review question for exam number 2 on Canvas. Click on exam number 2, download and print out that document, work on those questions. Okay. Answers for those questions are given at the end of the document, I believe. If it's not, let me know, I'll post it on there. I'll double check as well.